class where my objects know all this stuff, but they don't actually draw it until I ask it to. So that's basically a vector. It's an XYZ vector. But a cool thing about it is I use operator overloading so that we can actually add our vectors. So here we are in math class. We have these objects called vectors. Not only can we add them, we can multiply them. That's just scalar multiplication. You know, 3 times a vector makes it 3 times longer. If you negate a vector, I have a negate here, it just points it the other way. So if it was pointing that way, now it points that way. If you add 2 vectors, it does what you expect, and so forth. So we've got all the methods that you want. And because they're coming through a math objects kind of, they started with biotum and animal and dog, they're basically able to look at something like this and say, yeah, I see the rib cage. It's just like another creature. It's just like another animal. Vectors are just another kind of animal that happen to be in a math namespace. Okay, now some linear algebra textbooks, including one co-authored by Wayne Bishop, blah, blah, this stuff, all the vectors are defined that their tail is at the origin. You don't have vectors that start anywhere else. The only variable is where they point. So your tail is always the origin, and the point of your vector, like your arrowhead, is out there somewhere in space. End of story. So if you're going to do a polyhedron, like something nice around the origin, those are edges, like line segments. And they're not vectors because they don't start at the origin. So how do you define an edge? An edge is simply a pair of 2 vectors, one pointing to the end, one pointing to the other end. So this gets back to that SQL thing I was showing you in the first part of the talk. When we store a polyhedron, we need to get out those edges as vector pairs, which are tuples. And I often just label them with letters, single letters, because that's how geometry books have done it forever. Since time immemorial, we've labeled the points of a polyhedron A, B, C, D, E. And I do the same thing. So here we have an edge class, and all we're doing here is keeping track of 2 vectors. We're actually passing them in to instantiate it. So when I initialize an edge, I basically want my 2 vectors to come in, and go ahead and give me a color if you want. And the same thing, I defer drawing this in terms of a visual Python cylinder until I actually want the draw method. And then I can erase it. And now here I've got a plotter. You'd think that in spatial geometry, oh, we're doing vectors, it's 3-dimensional or whatever we call it. Why would we do 2-dimensional graphs in this context? Why not? In fact, I like always being in space, and forget about that special case where everything's flat. I don't like flat graphs because you forget there's a camera and you can go around the back. They always say the positive axis goes off to the right. Well, it doesn't go off to the right if you're standing on the other side. Very same graph, and you're on the other side looking from the back. But anyway, I like to be able to rotate my graph. So just last night, for example, I was trying to remember how this code works. The way I do my domains, you know how you do a graph, you feed in your x values and then you plot your y. This is just for simple xy plots. I use a generator to get my domain. So I have a starting point, say -8 on the x-axis, and then every time you go next, 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 it just increments by whatever increment or step you gave it. So it's solving that problem of how do you get little increments when you're doing kind of a discrete math approach to graphing. And then getting down more into calculus, it's so cool, like Steve was showing in his earlier lecture this morning, how you can just pass functions around top level in Python. That is such a cool thing. So when it comes to like taking the derivative of something, you can define the derivative, albeit in a discrete math context, in this very simple way where what you're returning is a function. In other words, I'm going to pass in a function. F is a function that I want to take the derivative of. And what I'm going to do is build a little function that uses that kind of standard definition of a derivative where I've preset my h, which of course is supposed to go to 0. I've set it to a very, very tiny, tiny number, 1 to the -5. So h is by default a very small number, and you can make it smaller yet if you want. And so I pass in a function f, and it builds a little derivative maker right out of that function and returns the function. So then my goal is to graph a function and its second derivative and its first and second derivative in Visual Python. And so here you see me setting up 3 domains. These are just generators, and all they're going to do is start at -8 on the x-axis and move forward by increments of 0.1. And then I'm creating a function here that is the output of the derivative function, where what I'm putting in is the bell curve expression. And I quoted this from a book I was reading last night, and this is, looks a little different when you see it in a math book, but like I say, this is a math notation. This is not an imitation. This is math. And what we're going to do here is plot this Mowbray thing that came out from 1738. It's fun to name your function something mnemonic. Use the guy's name and put a date. Why not? It helps people remember. So let's see. Let's just run this. See what it does. Remember, this is all using stickworks. In other words, when I get my graph, it's because I'm doing lots of little bitty edges. Little edge, 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 edge. This is all like vectors.